All right, we're ready to get started. Again, before we get started, you all know your second midterm is this Friday, November 22nd. So like what I did with midterm 1, I posted a announcement basically stating whatever you want to know about the second midterm. Well, it's Friday in this room, same lecture time, so just come as you would. The room is a little bit tight, but it works for midterm 1. It will similarly work for your second midterm. Midterm 2 will probably cover chapters 4 to 6, depending on how fast I finish. My goal here is to at least finish chapter 6.4, which is equilibrium calculations for ideal gases. If I didn't finish up on like reaction quotient and predicting the shifts in equilibrium, reaction equilibria, which is chapter 6.6, then we'll just cut at 6.4. So it depends on how fast I go. All right. Well, like midterm 1, 15 minutes, open book, open note. You can use whatever things you want, just nothing electronic. We will be printing out a appendix table for you, but you're feel free to use your own appendix table and your own formula sheet. Those are all free game. And the structure of the exam will be exactly the same. We'll have 10 true and false problems. We'll have 4 short answer problems and 1 comprehensive problem with multiple parts. So when you're practicing, if timing was a problem for you in midterm 1, make sure you practice it with the timer on. Like for example, each true and false shouldn't take you more than 2 minutes or more than 1 minute, and each short answer shouldn't take you more than 5 minutes. Like you know what to expect on the exam. I posted my last quarter's midterm 2 exam, but the coverage is a little bit different, so you'll see slightly shifted. Like last quarter, I'm not able to get it to chapter 6, so you'll see materials from chapter 4 in my previous midterm exam, but just because we're moving at a different speed. But the coverage of this midterm exam is from chapter 4 all the way to chapter 6.4 at least. All right, any questions on there? No? Okay, we're good. Let's get back to our materials. So we'll pick up from our last 2 lectures, right? So we spent 2 lectures talking about ideal gas mixtures, like what is ideal gas mixture, and how do we define chemical potential in an ideal gas mixture, and how did we define equilibrium constant for ideal gas mixtures. So today will be more or less like an application type of class. Like in all of our classes, right? So we spend lots of time talking about the abstract concept or definition of these terms. Then we spend some time deriving those abstract concepts into equations that we can use in solving chemistry problem. So today it's going to be phase 3, which is applying these equations that we derived into solving real chemical problems. So let's look at it together. Our goal here is to focusing on ideal gas equilibrium calculation. What does it mean? It means for a given ideal gas reaction, now by simply looking at the thermodynamic table, you should be able to predict what is the composition of my reaction mixture, saying like what's percentage of A, B, C, or D are in my reaction mixture after the reaction reached equilibrium. So there are several steps that we're going to go. So I'm going to go over all the steps with you, and then we'll do 3 practice problems together to see like how do we use these different steps and equations in different scenarios. All right, let's get started. So first thing, let's just review what we discussed. First thing first, that's the delta G naught equals to negative RT ln Kp. More or less, how did we define the equilibrium constant? And thinking about what are these terms, right? So my ln Kp, that is my pressure equilibrium, standard pressure equilibrium constant. Or my Kp naught, the equilibrium constant, is defined as a product of your partial pressure of different species I at equilibrium divided by the standard state pressure, which is 1 bar, to the power of its stoichiometric coefficient. All right, so this is a Kp naught So by its namesake, we're describing the equilibrium composition. So these are the partial pressure of each species at equilibrium. What about delta G? Delta G naught, that's the Gibbs free energy of my general reaction. Or the other way to put it is for a general reaction of 0 goes to stoichiometric coefficient times different species, we're defining our Gibbs free energy delta G naught at certain temperature equals to the sum of my stoichiometric coefficient times the Gibbs free energy of each species, the formation standard Gibbs free energy of formation of each species in my thermodynamic table. All right, so this is a fundamental equation that links our equilibrium composition to something that's tabulated data, to thermodynamic state functions. Step 1, right? What about the next one? How do we actually set up our calculated equilibrium composition? Well, first of all, you want to be able to calculate the delta G naught of the reaction. So this is pretty straightforward. We did that practice together, which, well, you read the appendix table and you plug in the numbers accordingly. Super nice and easy. Next up, using the equation of delta G naught equals negative RT ln Kp to solve for the equilibrium constant at 298 Kelvin. Now here is the first point that things might get a little bit more complicated. Note that the Kp naught here is the Kp naught at 298 Kelvin because in our thermodynamic table, my Gibbs free energy of formation are measured at 298 Kelvin. All right, so from here, and then we'll have one more step to take into consideration, which is a temperature dependence of your equilibrium constant on temperature. So that's what we did in our previous lecture through the derivation of the Van 't Hoff equation. All right, so in the Van 't Hoff equation, we derive that the differential or the change of your natural log of your equilibrium, standard equilibrium constant over temperature equals to delta H naught over RT squared. All right, so this one then have two different branches. Thinking about scenario 1, I'm just gonna focusing on this delta H naught here. Let me use different color here. So scenario 1, your delta T, the change of temperature is small. Let's say the delta T is smaller than 300 Kelvin. Within this range, we can assume that delta H naught is independent from temperature. All right, so within this range, let's say, for example, you were asked to calculate the equilibrium constant at 398, which is only 100 Kelvin. How do we solve for it? So for that, we can solve it by just doing the integral, right? So we have, so scenario number 1, so delta T smaller than 300 Kelvin. So what do we have? We have my D ln Kp equals to delta H naught over RT squared dt. So integration on both ends equals to the integration of delta H naught over RT squared dt. And then in here, we want to say because delta T is small, we assume delta H is constant. All right, right, so if you look at your chapter end problem, sometimes the textbook problem will say, hey, do the calculation, let's say calculate equilibrium constant at 398 Kelvin. State any approximation you're making in that process, and that's the approximation you want to write out. All right, and solving this integral, what are we getting here? Now, on the left-hand side, we have the delta ln Kp, or that equals to your ln Kp at T2 minus ln Kp at T1. On the right-hand side, we have my delta H naught divided by R. So these two are considered constants. I'm taking that out from the integral and to the integral of 1 over T squared dt. And solving this integral, that's delta H naught over R, which is 1 over T1 minus 1 over T2. All right. You can find these lecture notes on the end of our last lecture, by the way. So I'm just rephrasing them here. And if I'm copy-paste what we end up getting here, what we're saying is for small temperature change, we're saying the logarithm of your Kp naught at T2 over Kp naught at T1. So that minus, we put it into the natural logarithm. That becomes the natural log of Kp naught at T2 over Kp naught at T1. That's roughly equals to delta H naught divided by R, 1 over T1 minus 1 over T2. All right, now this is when delta T is a small number. Small by, say, delta T is at least smaller than 300K. It's quite arbitrary. Like, we will make sure it's super clear. It's either like only 100 Kelvin difference, or it's like more than 1,000 Kelvin differences. So you're clear to know like what equation you want to use. Scenario 2. So now what if we have a big delta T? So this actually links back to our previous discussion in chapter 5 when we talk about temperature dependence of delta H naught. And in that lecture, we went over the discussion of the integration of your d delta H naught, the molar enthalpy between T1 to T2 equals to the integral between T1 to T2 of the delta Cp naught dt. All right, so it's related to the heat capacity and how does the heat capacity change with respect to temperature. Now, typically, we'll give you that equation of like what is Cpm as a function of temperature, or what is delta H naught as a function of temperature. It's very likely to be a polynomial equation. So we'll probably have something like delta H naught at certain temperature equals to like A plus BT plus CT squared all the way through, right? So it's nothing like specific. I'm just highlighting this here is when the delta T is big, you'll need extra information. Either we give you information with respect to the isobaric heat capacity, or we give you additional information regarding how does delta H change with respect to temperature. All right, so this is our step number 2. This is one of the steps that looks straightforward, but there are lots of things that can go wrong in this process. The whole point here is how to calculate the equilibrium constant, or the pressure equilibrium constant in this specific example. How to best calculating equilibrium constant. And especially when temperature is different, like keep in mind, this equation only gives you equilibrium constant at 298 Kelvin. And use the appropriate equation to translate that information into the appropriate temperature and calculate the equilibrium constant. All right. Step number 3. Now we have the equilibrium constant, and we know that equilibrium constant, well, it's defined as the product of your partial pressure at equilibrium over P naught to the power of your stoichiometric coefficient. So we want to express the equilibrium Mohr numbers, or how much number of Mohr of your different reactant or product or relevant species at equilibrium. So here we're saying the Ni equilibrium, or if I put it out, that's the N number of Mohr of substance I at equilibrium. And naturally that equals to your initial number of Mohr of substance I. So this little 0 means that's the initial number of Mohr of your species. And plus the stoichiometric coefficient times the extent of reaction, or this is your change in the process. Right, so stoichiometric number is negative for a reactant. That's why your equilibrium number of your reactant will be smaller than your initial number of Mohr of your reactant. And this one, again, that's our stoichiometric extent of reaction at equilibrium. With the number of Mohr of each species we know, we'll be able to express the equilibrium partial pressure, Pi, as a function of your extent of reaction, C. And also, like in this case, how do we do it? We know that Pi for equilibrium mixtures, for ideal gas mixtures, equals to chi I times the total pressure P. Right. And then we plug in our calculated or expressed partial pressure into the equation to solve for the extent of reaction, C. And then plug in the C back into the initial relationship to find out what is the equilibrium composition. All right. So far, so good? So that's the general gesture. So now let's just look at 3 different examples together. So basically, we're going to work on all these examples together and see what are we getting. It's last lecture. Okay, so quick question here. How do you want me to do it? I can do it on my iPad, but the problem is I won't be able to show these lists for you, or I can do it on the board, so I can quickly come back to say like which step I'm using, which one will work better for you. Okay, I'll just do iPad then. All right, so here's the example. This one is a more straightforward one. You can think about this as your Gen Chem review of, let's say we give you a reaction of your ammonia formation, and then we give you the starting initial number of Mohr and ask you to calculate what's the equilibrium number of Mohrs. Or how to express the reaction quotient based on the calculated partial pressures of different species at equilibrium. And we'll talk about reaction quotient later on when we actually get to chapter 6.6. So just get started looking at a review of our ICE table. So initial number of Mohr, let's say we start from 1.0, 2.0, and 0.5 for your nitrogen, hydrogen, and ammonia. So the change of number of Mohr here, depending on the stoichiometric coefficient. So this one is -1, -3, and +2. So, yes?
How come for the equation is NH2?
What equation?
The equilibrium equation.
It is H2.
Yeah, but then on the table is NH3.
Oh, this is the product. Oh, sorry. That should be NH3 as well. Thank you. All right. So again, this is what we want to do, putting the numbers there. So the change of number of Mohr in the processes, we have that equals to mu I times extent of reaction. So for N2, that's -C For H2, that's negative 3C. And for NH2, that's just 2C. Right, so at equilibrium, we'll have N2 is 1 minus C. H2 is 2 minus 3C. And for NH3, that's 0.5 plus 2C. All right. The total number of mole at equilibrium, thus we can calculate it to be N total number of mole at equilibrium is the sum of the number of mole of your species I at equilibrium. So basically you add all three of them together, and our result here becomes 3.5 minus 2C. And let's say for this reaction, we're keeping the pressure not changing. So we'll be able to calculate Pi equals to chi I times pressure. And that equals to each of your number of mole of your species at equilibrium over total number of mole of species at equilibrium times the total pressure. This one is a quick review in like what do I mean when I say use the ICE table to translate the number of mole of your species into your partial pressure. And now let's do the real example, which might be a little bit more complicated. So here, imagine we have a system that we tell you initially contains 3 mole of N2O4 gas, 0.5 mole of NO2 gas, and also we give you the total overall equilibrium of this process. Both of them are behaving as ideal gases. And we're telling you the equilibrium is achieved at 25 degrees Celsius and 2 atm. Now here is the one more important information, as we already know that temperature equals to 25 degrees Celsius or 298 Kelvin. So we can directly use our tabulated data, and we do not have to use Ventov equation. But we can, if we're changing this into like 50 degrees Celsius, then we have to use the Ventov equation to solve for the process. And also it asks us to find the equilibrium composition. So let me just copy paste what we have in the problem here, so I can keep using my iPad to go over the problem with you. This should be quick. So the reaction we're looking at is N2O4 as a gas in equilibrium with 2 NO2 gas. We read the question, we see that the initial number of mole of my N2O4 initial equals to 0.3 mole. The initial number of mole of my NO2 equals to 0.5 mole. And we know that at equilibrium, we have temperature equals to 298 Kelvin, pressure equals to 2 atm. The question asks us to solve for the number of mole of your N2O4 at equilibrium and the number of mole of your NO2 at equilibrium. All right. So basically, this is how I read a question whenever I see something like that. I just write down like what are the things I know and what are the things I need to solve for. Okay, and now let's actually do this problem together. Remember our 6 step. First step, use the tabulated data to find out the delta G of the reaction. Right, so this should be pretty straightforward. You read the table, and there is a typo here. You read the table and use the equation, which is a delta G naught at 298 Kelvin equals the sum of stoichiometric coefficient times the standard formation of Gibbs free energy. So I have my delta G naught at 298 Kelvin equals to, well, we have 2 in front of my NO2, 2 times 51.31 minus 1 times 97.89. And that equals to 4.73 kilojoule per mole. Next step. Use delta G naught equals to negative RT ln K to solve for your equilibrium constant. Well, so let's see. R is a constant, T is a constant, and we know what delta G is. It's just plugging numbers to get a numeric number. So that becomes 4.73 kilojoule per mole equals to negative 8.314 times 10 to the negative 3 kilojoule per mole. So this one, make sure you're using the same unit in your gas constant. Times 298 Kelvin ln Kp naught. So we solve for natural log of Kp naught to be equal to negative 1.909, and your Kp naught equals to 0.148. So I can just put it in here. It's like what we solve for is Kp naught at equilibrium at 298 Kelvin equals to 0.148. All right, so step 3. Step 3 is we want to express my equilibrium mole numbers into a function of your initial number of mole and also your stoichiometric times the extent of reaction. So that's what we did in our practice. At equilibrium, we have number of mole of N2O2 at equilibrium equals the number of mole of your N2O2 initial plus the stoichiometric coefficient of N2O2 and times the extent of reaction. Right, so plug in the numbers, we have that equals to 0.3 minus the extent of reaction. Same applies to my product, which is NO2 here. So number of mole of my NO2 at equilibrium equals to my initial number of mole of NO2 plus stoichiometric coefficient of NO2 times the extent of reaction. So that's 0.5 plus C. Okay, so that's 0.3 minus C, 0.5 plus 2C, sorry. All right. Well, and now we have all these numbers. We just set up my ICE table to see what exactly is the equation we're solving for. What is C? Well, so this is, again, at constant Tp. And we can solve this to be number of mole. We have N2O4, NO2. We'll write my initial delta N and N equilibrium. This is, again, how do we do it? You can do it in different ways, right? So this one is, we start from 0.3, 0.5, negative C, 2C. This is 0.3 minus C, 0.5 plus 2C. And we end up getting the total number of mole at equilibrium equals to 0.8 plus C. So that's the addition of the two equilibrium composition. And from here, we can write out the expression of partial pressure, which is my partial pressure of NO2 at equilibrium equals to the mole fraction of NO2 at equilibrium times the total pressure, and that becomes my 0.5 plus 2C over 0.8 plus C times my pressure. And note that, what is my pressure? my pressure is at 2 atm here. Likewise, we can do the same for our N2O4 at equilibrium equals to the mole fraction of N2O4 at equilibrium times the total pressure. That becomes 0.3 minus C over 0.8 plus C times the total pressure. All right. Well, what else do we know? We haven't used our equilibrium constant, so now we're going to use the partial pressure we solved for, write my equilibrium constant from the definition and solve for my extent of reaction. So plugging these two numbers into my equilibrium constant, we then have my Kp naught equals to P NO2 at equilibrium divided by P naught to the power of its stoichiometric coefficient times the partial pressure of N2O4 at equilibrium over P naught to the power of N2O4 stoichiometric coefficient. So this is one thing that people tend to miss, especially when the stoichiometric coefficient is not 0. So keep in mind to add this power on there. And then just plug in the numbers. All right, so we have 0.5 plus 2C over 0.8 plus C, P over P naught. This is, again, a easy to miss point because my P naught here is 1 bar. So this is the 2 atm into 1 bar. So there is a unit conversion inside the bracket to the power of -1. And then here we have my 0.3 minus C, 0.8 plus C. Likewise, times P2, P naught to the power of 2. Or I think I got it wrong here. This should be 2 and this should be -1. Yeah, I was plugging the wrong number. Sorry for that. Yeah, so this is the product. This is the reactant. All right. So two things that's easy to miss in this step. The first thing is make sure you're converting the unit of your partial pressure into the actual unit and also your overall pressure. And secondly, make sure you include your stoichiometric coefficient in there with the correct sign. And then it's just solving a quadratic equation. So I trust you all have a good enough calculator for it. If you do not, I highly recommend you get one calculator ready for the exam to solve this kind of equation. You don't want to do it by hand. We'll also try to have like a scientific calculator for you to borrow if you want. And solving the quadratic equation, like we know Kp naught here equals to 0.148. So if we solve this quadratic equation or get my C, have two different answers. One is negative 0.324 more or negative 176 more. And typically, in this case, we'll only have one result that is physically meaningful. Like, for example, in this case, if we say we calculated my C equilibrium equals to negative 3.4 more. Now, in this case, if we look at my NO2 with a stoichiometric coefficient of 2, the maximum number of C we can get is 0.5 divided by 2, so 0.250. Now this one is smaller than my 0.250 and hence not a valid answer or an unphysical answer. Yeah.
Where did 0.250?
0.5 divided by 2. And at the very end, now we have solved for my C equals to, and by the way, this 0.5, this negative 0.25, why we're using the product is the negative extent of reaction is demonstrating the reaction is a reverse reaction. So my NO2 is the real reactant. It doesn't matter how we draw it, like the sign of the extent of reaction, that's a demonstration of what's the real movement of my equilibrium, right? So in this case, we have a negative in front of my extent of reaction. So my NO2 is a real reactant. We only have 0.5 more of NO2 available in the mixture, so that negative 324 is unphysical. Like we do not have, it cannot take place. It's not possible. All right. And obviously, next step is just plugging what we calculated, which is C equals to negative 0.176 more, and you plug in to these numbers to get your final number of more, or the equilibrium composition. Let me just finish doing that. So number of more of your N2O2 at equilibrium is 0.3 minus C equals to 0.476 more. Number of more of NO2 at equilibrium will be 0.5 plus 2C equals to 0.148 more. Like this could be a very straightforward, comprehensive problem. Not necessarily in this exam, I'm not saying that. But like, for example, the first part could be like solving for your equilibrium constant at a different temperature, and then use whatever we did to solve for the equilibrium composition at that condition. And also at the very end note, we might also ask you in which direction this equation is moving. So that's depending on the sign of your extent of reaction C. So I went this very slowly with you. I hope this is a good enough demonstration into what exactly do we mean when we say solve for equilibrium composition. All right, so this is one of those examples that you get a numeric answer based on our understanding of the equilibrium constant, delta G of the reaction, and the extent of reaction. The next example will be more or less calculating something that's coming up with an expression, right? So in this case, we're giving you that the gas phase isomerization reaction of, now you have A, B, and C. All three of them are in equilibrium with each other. You have A to B, A to C, and B to C. You have three different equilibrium taking place in that reaction mixture. We tell you the reaction reaches equilibrium at a fixed temperature T, so some temperature. We don't have to solve for numeric answer. And we ask you to express equilibrium mole fractions of A, B, and C in terms of equilibrium constant. So for this kind of question, how do we approach it? First thing first, we do this kind of analysis to say, like, what do we know and what are we solving for? So what do we know? So let's just write out what do we know. We have three different equilibrium taking place, so A to B. Now we can write my equilibrium KBA equals to my PB over P naught, PA over P naught. And for ideal gas mixtures, my PB and PA equals to my chi BP over P naught, chi BA over P naught. Right. Since the stoichiometric number is exactly the same for my equilibrium constant that's given in the problem, we can replace it to say like 2A goes to B or 2C goes to A or etc. Now in this case, because my stoichiometric coefficient is exactly the same, we can write that to be chi B over chi A for the equilibrium between A to B. The same analysis works for all other two equilibrium, like A to C. We can write my K CA equals to chi C over chi A, and my B to C equals to my K CB equals to chi C over chi B. And note that all these mole fractions, we're talking about the equilibrium mole fractions. All right, so this is what we know. What else do we know? We also know that my my more fractions at equilibrium will add up to be 1. We only have 3 things in there. So naturally, we have chi A plus chi B plus chi C equals to 1. We only have 3 things in the mixture, so the more fraction must add up to be 1. All right. So what the question is asking for? The question is asking us to express my chi A, let's say, as a function of my k BA, k CA, and also k CB. Right? You don't have to use all 3 of them, but we're saying we're looking for the expression of my more fraction as a function of your 3 equilibrium constants. How do we do that? Well, so let's say we start by writing out my process here, right? So in this case, we're looking at chi A plus chi B plus chi C equals to 1. So what if we can express my chi B and chi C using a function of chi A and the equilibrium constant? So we're using this 2 relationship here. What do we have? Now, in this case, the first one, we have chi B equals to chi A times k BA. For the second one, we have chi C equals to k, well, chi A times k CA. All right. And we can plug in these 2 expressions into something we know, which is all 3 more fractions adds up to be 1. And that equation effectively becomes my chi A plus, well, chi A times k BA plus chi A times k CA adds up to be 1. And again, this one just equals to my chi B. This one is my chi C. So do we have our answer? Right. We just want my chi A as a function of all 3 equilibrium constant. So now we have our answer, first of them, which is chi A equals to 1 divided by your 1 plus k B over A plus k C over A. Doing it? What about chi B and chi C? Now do we have an expression of it? Someone want to take a guess? We already have the answer. Right, so if you think about it, we have already expressed my chi B as a function of chi A times an equilibrium constant. So likewise, we have 2 pieces, right? We express my chi A as a function of equilibrium constant. We know my chi B is my chi A times an equilibrium constant. So my chi B, well, equals to my k BA over the equation that we just derived, which is 1 plus k BA plus k CA. All right. And likewise, we can express my chi C equals to my k CA divided by 1 plus k BA plus k CA. And in this question, there are different answers that are also correct. Let's say in here, I randomly picked, I want to start from chi A. Right? What if I randomly pick that I want to start from chi C? Then, well, we want to use this one, which is the C and B and C and A, and then we'll have a different expression. So we'll end up to have like 3 possible expressions that are effectively the same to each other. And also these equilibrium constants are also interconnected with each other. But that's a little bit go beyond what I wanted it to be. All right, so I hope like today is a good example of how can we apply everything we discussed so far into questions of solving, of making a connection between equilibrium constant, equilibrium composition, and thermodynamic table. We went over 3 different types of problems. First one is a very straightforward short answer type of problem, which you just plug in the ice table, you solve for the partial pressure. Second one is a more comprehensive style. We're using all 6 steps that we went over, right? So how to calculate the delta G of the reaction from tabulated data, how to translate that into equilibrium constant. We did not do an example of the temperature dependence, but these are things we discussed before, and we did that example here, right? 2 different scenarios. Delta T is small. You can directly use the Van 't Hoff equation. Delta H is big. You want to look for information regarding how does the delta H or heat capacity change with respect to temperature. And then how do we set up your calculation by expressing your number of mole of your species at equilibrium using initial condition and also your extent of reaction C. And also like at the end, you can calculate the equilibrium mixture. And in this process, we also demonstrated that the direction of the reaction, it doesn't matter how do we draw it, right? What is the real reactant depending on, well, the combination of your stoichiometric coefficient and the extent of reaction. It can be backward reaction as well. And then at the end, the example we just did is something like, instead of getting a numeric answer, how do you set up your process into solving these kind of seemingly abstract problem? My strategy is always I write down what I know, I write down what is needed, and see how do I connect them. Okay, I have only 3 minutes. I don't think I'll keep going. So your midterm exam will cut to any point all the way until like 6.4. 6.5 is plotting using Excel, so that's not applicable for our midterm exam. But we'll pick up next Monday on 6.6. And on Wednesday, we'll do a buffer lecture, which is reviewing things together. And since it's been a while, I think I'll be focusing on chapter 4 materials, because, I mean, these are still pretty fresh with you. So I'm not going to do more example on equilibrium mixture, but it doesn't mean it's not going to be on your midterm. It's just like I want to refresh your memory on chapter 4 and 5 a little bit more. All right, that's all from me today.